Okay, well, welcome back. It's been a few years since I recorded, and in the meantime, I have changed my university. I've moved to a different state in the United States, and it is 2020, the year of coronavirus, so we don't record in TV studios anymore, but at home. But this is a learning experience for me too, and so let's give this a try. There are a few holes in the sequence of lectures that I recorded many years ago, 6 or 7 years ago now. And so what I would like to do is fill some of these holes, and the lecture in particular that I would like to record now and a few more in the next few days are about the question, well, what is the finite element really? And the course that you're watching, all of these lectures together, are not really meant as an introduction to the finite element method, but it is worthwhile talking about some of the fundamental ideas, the sort of things that make the finite element method work, that have shown over the last nearly 70 years now that this method actually works. It works very well in practice, and so it is worthwhile to think about what is behind this method that makes it tick. And so in the next few lectures, I would like to talk to you about the two big ideas that underlie the finite element methods, namely polynomial approximation and the weak formulation, and a little bit about the theory too. So it's worthwhile to see a few statements of mathematical convergence, for example, that illustrate why this method is so successful. So let's go straight to this. So it is about the ideas behind the finite element method, and in particular, what I would like to talk about is the approximation. So when we talk about the partitive solution of partial differential equations, for example, like the Laplace equation that I have here on the slide, the Laplace equation in 2D minus Laplace u equals f, together with boundary values that could be Dirichlet values like here, then what we really mean when we say that we want to solve it is that we're looking for a function u of x and y. And so when somebody says that they know the solution, u of x and y, what that really means is that we have to have a way to be able to say what is u of x and y at infinitely many points x and y, because there are infinitely many points in this domain. And so when I phrase it like this, it already becomes clear that there is probably an issue, right? When I say infinitely many points, that is something that we will struggle with in practice. Namely, computers can only store finitely much data. My laptop here has, I don't know, 16 gigabytes of memory, I believe. So that's all that I can store. I cannot possibly store the solution I cannot possibly store the solution, because to know the solution, remember, requires me to be able to say what the value is at infinitely many points x and y. So I cannot actually store the solution of a partial differential equation. And the second part, of course, is that I cannot compute it either, because in order to compute infinitely much data, it will require me to do infinitely many operations. That too cannot work. And so there are fundamentally two consequences from this observation, namely, we cannot, in general, solve PDEs exactly. It just does not work. It requires us to represent a function that has infinitely much information amount, and that is something that we cannot do. And the second consequence is that the best we can do, the best we can ever hope to do with partial differential equations is that we approximate the solution somehow. So approximate means maybe I don't get the exact solution, or I cannot represent the exact solution, but I can come close. I can find a function that is close to the exact solution. And so the question then becomes, well, how close is close, and how much data do I have to store and compute in order to be less than 0.01 away from the exact solution, and so on and so forth. So there are questions that follow from this. But fundamentally, the best we can do is to approximate solutions of partial differential equations. So in this and the following lectures there are fundamentally two questions that we will need to answer. Namely, what is the best way or what is a good way to approximate functions that requires only finitely much data and computation? So there are, of course, many different ways how I can think about approximating functions. And then the second question is, once I have identified a good way to approximate functions in general, how exactly do I solve a PDE in the sense of actually computing an approximation for it, right? It's not just knowing how to approximate in general, but find a particular approximation of the solution. So these are two questions that we will have to answer. And this lecture in particular is about question one, namely, what is a good way to approximate functions? So there are many different ways how you can approximate functions. You've seen, for example, that you can use a Fourier decomposition. So typically you would say, well, we know Fourier tells us that if the function satisfies certain properties, that I can represent any function by an infinite Fourier series. Now, infinite doesn't work, but we can approximate the function by truncating after a certain number of points or for a certain number of terms. So I get a finite Fourier series. There's also Taylor, who tells us that I can do a Taylor expansion, and that if the function satisfies certain properties, that an infinite Taylor series, for example, will also approximate this function. And infinite, again, doesn't work, but I can truncate this series after a certain number of terms. And the third option would be that I split up my domain. So think about a one-dimensional domain for a moment. I can split that into little intervals. And on each one of these intervals, I do one of these. I could do a Fourier series, or maybe I could do a polynomial approximation. But I choose one approximation here, and I choose another approximation on the next interval, and another approximation on the next interval, and so on and so forth. And it will turn out that for many good reasons, the finite element method uses option number 3, namely it splits the domain into intervals in 1D, or in 2D, and in 3D I split it into what we call a mesh. So that's a collection of triangles or quadrilaterals, for example, in 2D, and in 3D maybe a collection of tetrahedra and hexahedra. And on each one of these cells that constitute the mesh, I'm going to find myself a polynomial approximation. And so in order to understand why that is, one of the two key insights that make the finite element method work, let me walk you through why options 1 and 2 are not particularly good. So fundamentally, it comes down to the following. When you have a PDE, then solutions typically look like this. So this is the pressure in Stokes flow in a domain with a corner. And you see that in this case, the pressure actually is unbounded. It has a singularity that makes it go to plus infinity and minus infinity. And that is a typical feature of solutions of PDE, that they often have singularities at corners. So there are certainly places that we can anticipate are going to be difficult to approximate here in the vicinity of this corner. But then, of course, also over here, the solution is actually extremely smooth, right? And so you would expect that in these areas, approximation is actually really simple. We just need to find a way to approximate it somehow there, and it's probably not going to matter terribly much how we do it. But this is going to be the problem here, that the function has a singularity at this point. Here's a second example. So that's an example of neutron flux in something like a nuclear reactor. For example, you've got neutrons coming in from the left, and then there is an area here where there's an absorber. So think about an obstacle to the neutron. And you can again see that, well, so there's much variation. In this area, the solution might have a kink here. There are sort of corner problems. But in much of the rest, actually, the solution is nice and smooth. And so, again, we will have to have trouble with approximating these sort of functions if we don't pay attention to the fact that the behavior in some parts of the domain typically is much, much worse than in most of the other parts. So these sort of observations up, what you typically find in PDEs is that solutions are smooth in large parts of the domain, that they vary greatly in small parts of the domain. They might have kinks or singularities. And just to put that into context of what you probably know, if you're an engineer, for example, you think about loads and displacements and stresses. So here's an example of a plastic piece that it has been deformed, and so these interference patterns that you see here, they give us an indication of the stress, and you see that there is a stress singularity here just because you can see how these bands become more and more and more narrow. So stresses typically have singularities. That's the place, of course, where cracks form. So it's these sort of things that we have an intuitive understanding of how these solutions look like. Cracks happen in exactly those places where the stresses go to infinity, for example. So the fact that solutions of PDEs look like this should not really come as a surprise if you have thought about, let's say, how bodies deform, if you remember the connection between displacements and stresses, for example. All right, so let's look at why Fourier approximation, for example, does not work very well. So we know that under certain circumstances, you can represent a function u of x as a sum of sines, and maybe cosines is not important here, but you can represent them as a sum u1 sine x plus u2 sine 2x plus u3 sine 3x, and so on and so forth, and maybe the corresponding with the cosine terms. We also know that this is a good approximation really only if this function u of x is globally smooth. There's two parts to this. It has to be smooth, and it has to be globally smooth. It has to be smooth everywhere. So to give you an example, so here's a function that is a step function here, okay, and I'm going to approximate that with more and more and more sine terms. So the first picture here shows one sine function. This one also takes sine 2x and sine 3x into account. This one takes sine 4x, sine 5x into account, and so on and so forth. And the important observation here is that even though these discontinuities happen only in certain places, the solution is actually oscillatory everywhere. So the takeaway message of this is that even though the problems with the function are very localized, with the original, with the exact function, with the blue function, the red function, our approximation, is bad everywhere. And so what that means in the context of PDEs, that if you, for example, have a singularity somewhere, you will have problems with your approximation in the entire domain if you use sines and cosines, if you use a Fourier approximation. And so as a consequence, that does not actually work very well. I mean, people try it, people use that in certain circumstances, but generally speaking, the problem with these localized singularities is destroying the approximation properties everywhere. So if Fourier doesn't work, maybe Taylor works. So you could say, okay, so I'm going to represent my function u of x as a sum of Taylor terms. So u0 times x minus x naught to 0. So u0 times 1 plus u1 times x minus x naught plus u2 times x minus x naught squared, and so on and so forth. So we know, again, I can do a Taylor expansion around the point x naught, for example. And you might also think, okay, so maybe not Taylor expansion, maybe I can do a global polynomial that is defined in some other way. But the important part, again, is these sort of approximations really only work in the neighborhood of a point x naught. So if you take, for example, the sine function, this black curve here, so if I take the constant and linear term, I get this red approximation. And it's a good approximation here in this vicinity, but it's pretty bad over here, right? The function is much, much larger and certainly not close to the black curve. All right, so you say, in addition to my linear term, I'm going to take the quadratic and cubic terms as well, and I get this orange curve here. And that's a better approximation, but way out here, still not good. 5 terms, 7 terms, 9 terms, 11 terms, 13 terms, the area of approximation becomes larger and larger, but at the same time, where it's not a good approximation, these functions become even worse approximations than the red one, for example. And so again, what we learn from this example is that making the polynomial degree higher and higher and higher really globally still leaves a very difficult approximation problem. And what I don't show here is if you go back to, for example, the step function, of course, if you locally approximate, the approximation is only good within an area where the function is actually smooth. if a function at some point becomes infinite or has a discontinuity or something like this, you cannot expect that the Taylor approximation is actually very good. So, for example, to illustrate this in terms of theorems, so if this function u of x is bounded, then we know from the Weierstrass approximation theory that every function can be approximated arbitrarily well by polynomials. So that is not necessarily a Taylor approximation, right? But what Weierstrass says is every function that is bounded can be approximated by polynomials. But you've seen that some of the solutions of PDEs are not actually bounded, so we cannot expect this to work. And to make this a little bit worse, so if you have a function that has derivatives with kinks, right? So I showed you the neutron absorption problem where you have a function that is going to have a kink, then global polynomials will be globally bad, just like the Fourier terms. So Taylor approximations, or in general, global approximations of functions only work if a function is in fact globally smooth. So it cannot have kinks, it cannot have singularities. All of these things will destroy the approximation, not just in the vicinity of the singularity, but in fact everywhere. So the solution to this conundrum is what we call piecewise polynomial approximation. So I'm going to split my domain on which I want to approximate this u of x into small parts, and then separately approximate the function on each part. So for example, here I want to approximate this green sine function. I split the domain into 1, 2, 3, 4 intervals, and on each interval I'm going to approximate the green function by a piecewise linear function. Piecewise linear means that on each interval it is linear. Okay, so on this leftmost interval here, I have one linear function that in this case interpolates the green function. Interpolation means it is equal to the original function at a number of points. So in this case, at this point and at this point. And on this next interval here, I have again a linear function that is equal to the original function here and here. And so maybe that's not such a great approximation here, but I can continue this. So I can refine the mesh once more. So that means I replace each interval by its two halves. And you see that in this case, this piecewise linear approximation, this purple curve, is already much better than what we had before. And I can continue this. And so here now, you can hardly see the difference between the original function and the piecewise linear approximation. And you can imagine that I can do something like this in 2D as well. So I start with the screen surface here. Again, the purple is a piecewise linear or bilinear approximation. And if I continue this refinement process, I'm going to get something where the approximation looks very similar to the original function. So that works pretty well, and because the approximation happens on each of these subintervals, or in 2D on each of these cells, so a cell here would be, for example, each one of these little squares where I find myself an approximation, it's relatively easy to understand that if there is a singularity somewhere in the domain, well, maybe the approximation on the cell that is around that singularity is going to be bad, but everywhere else I can hope that it is actually reasonably good. So that's sort of the idea of this piecewise approximation, that I can isolate the problems. That if there are problems, if there are parts of the domain where the solution is badly behaved, I will get poor approximation quality there, but everywhere else, I can hope that at least things work out well. So the advantages of this are that when you use these sort of piecewise approximations, I can use low-order approximations. So I can use piecewise linears. Or maybe I'm going to approximate with quadratic functions, but relatively low-order polynomials. And as you've seen from these examples, if I make these intervals small, then I will get good approximations. Okay, so that is already an important realization, that if I put in more work, right, small intervals means I have to compute more, I have to store more information, right? But if I put in more work, I will get in a better approximation. And then it is insensitive to the singularities because I can isolate the poor approximation to those cells where the singularity actually lives. And then in practice, it is relatively easy and stable to parameterize low-order polynomials. It's also easy to evaluate polynomials. So if you think about if I had sines and cosines, it's computationally actually quite expensive to compute the sign for a given argument. Because, well, what exactly is a sine? Well, it's defined through its Taylor series. Whereas for polynomials, the only operations that I have to do in order to evaluate a polynomial at a given x is to do additions and multiplications and maybe some divisions of floating point numbers. So it's relatively easy to evaluate. And if I use something like the Horner scheme that you might have learned about in the introduction to numerical analysis, it's also stable to do this. So there are other things that I can do with piecewise polynomials. So in particular, if I have kinks and singularities, I can approximate it locally. So I can isolate the problems, okay, independently of what happens in the other parts of the domain. And then I can do something that is called H-adaptivity that you will learn about in later lectures. H-adaptivity means, well, if I have areas where my solution has a singularity, or is rough, or has a kink, for example, maybe these are the areas where I need small intervals so that I can closely follow the solution there. Whereas in other parts of the domain, and you've seen that that typically happens, in other parts of the domain, the solution will be really smooth. And in those areas, I probably don't actually need small intervals or small cells. So I should be able to come up with a mesh with a collection of intervals, a collection of cells in 2 and 3D, where the cells are large in a fairly substantial part of the domain and small only in those areas where it is actually necessary. So I can locally increase the resolution, and that makes computations substantially cheaper, maybe 10 times in 2D, maybe 100 times cheaper in 3D, for example. So this piecewise approximation helps me because in order to get more accuracy out of my approximation, I do not have to globally increase the polynomial degree. So here's an example of how this looks like in 2D. So you have, for example, the exact solution. This is taken from step 6 of the deal.II tutorials. So you have a solution that has a kink along this edge here. And you see that in order, or you can anticipate that in order to accurately represent the solution, I might want to have very small cells here in the vicinity of this kink. Whereas in these areas around and maybe in the middle, I do not actually need large cells because the solution is nice and smooth, and a low order approximation on large cells will still be a good approximation. So on the right here you see an approximation in the coarse mesh. And you see that there is, of course, a substantial difference between this approximation and the original solution. But if I refine this a number of times, then I'm going to end up with something like this. So you see that I have small cells here in the vicinity of this kinks, large cells in the middle, and large cells on the outside. And this is actually a quite good approximation to the exact solution. So this illustrates this approach of H-adaptivity. Oh, here's another mesh that is even better. Similarly, I can use a process that is called P-adaptive mesh refinement. So P-adaptive mesh refinement is typically intended as a way to make the solution more accurate. And what it means is that in areas where the solution is nice and smooth, so if you remember the pressure for the Stokes equation, for example, there were large areas where the pressure field was very smooth. So in those areas, if I have a large cell and I use a piecewise linear approximation, I might get a decent approximation. But because the solution is smooth there, if I use a quadratic function, for example, I would get something substantially better. And maybe I can use a cubic or a quartic polynomial on that cell and make it even more accurate. So that's sort of the idea of P-adaptive mesh refinement, where I choose the polynomial degree P on every cell individually. And that is also one of the things that I can do with piecewise approximations. So the takeaway message of all of this is that there are many ways to approximate functions, and which one is appropriate depends on sort of the class of functions that we're interested in. And that for finite element, for the solutions of partial differential equations, the solutions typically have a structure that does not make it amenable to, let's say, a Fourier or a global polynomial approximation, but instead that you want to use something that corresponds to a piecewise polynomial approximation on the subdivision of the domain into small intervals or small cells, because that is accurate, stable, it is flexible, it can do H and P adaptive mesh refinement, and it is relatively easy to represent in data structures. And so, given this sort of idea of piecewise polynomial approximation, then what we should do in the next few lectures is first to consider, well, how accurate do we know from theoretical considerations are these sort of approximations? And then, of course, well, how do I actually find one, right? So I do not know the exact solution, of course. If I knew, then I didn't have to use the finite element method. So given that I do not know the exact solution, the question, of course, becomes, well, how exactly do I find the solution? And that will be sort of the program for the next few lectures. And I think with this new experiment,